I'm Lo, which is the optical application engineer from Cybernet System Malaysia. So I would like to start the webinar with the title of the callback cache update, the Photonic integrated circuit design. So the design will be in the PAM, the pulse amplitude modulation device. So this is the agenda. So first we will go into the Ansys introduction. So second, we will go do the design challenge and the workflows about the photonic integrated circuit design, the WDM PAM. So the part will be covered on the photonic and optical simulation. And next we will go to the multiphysics simulation workflow. So first we will introduce the Ansys. So here is the multiphysics for the complex system design optimization. So in Ansys, we cover the simulation physics about the structure, fluid electronic, semiconductor, optical, and the 3D design and photonic. Okay. So here is the global simulation strategy. So the Ansys is the largest software simulation provider in the world. So as we know here, the Ansys already acquired few couple of the optic and photonic software. So first acquisition is the optics, which is the pure. The acquisition is in 2018. So the pure is the system level ray tracing tools. And next in 2020, Ansys also required the numerical, so which is the photonic solver. So most of the simulation and the design, the nanometer scale, and the geometric using the full wave simulation technical. And finally is in 2021, the Ansys acquired the GMAX, so which is the sequential and non-sequential ray tracing tools for the optical component optimization. So it's emphasizing on the imaging system. So here is the multiphysics in the optics and photonic portfolio. So in the numerical, we use for the design in the chip level, like the waveguide, sensor, and also the micro lens. And next we go to the macro size using the ZMAX, which is making the lens stack and also the optomechanical tolerancing for the optical component modeling. And lastly, we will combine the result from the numerical and also the GMAX to make a system level modeling. So we can make actual the real human vision and the perception and also the 3D environment integration to see the actual result. So next is the benefit to using the Ansys optical solution. So since just now we mentioned the multiphysics, so we have a complete set of the tools, optical and photonic, to make the product development process. Also, we have the product and development support on the simulation. And lastly is the workflow. Besides, we send the data between this optical and photonic CAE. We also can combine two others, such as the electronic desktop software. So we also can make the thermal analysis and also the high frequency analysis. So here we will start the title for the overview and also the design challenge of the core package optic application, which is the 4-channel wavelength division multiplexing for the 4-level pulse amplitude modulation transceiver design. So in here, this is the challenging. So along the rapid growth of the photonic, so this create the new opportunity and also bring a lot the new challenge for this PIC design. So for example, we will see this big transition for the design focus on the component to the circuit and system. So and we definitely need a different tools for this different design purpose. So but we also want them to integrate it together well. So Ansys will provide a platform. We can cover all the physics just in one workbench. Then we can transfer all the simulation result and simulate into a system. Okay. So with the above mentioned challenge in the previous page, so the consequences will come with like need to switch between the different tools. So this will cause the user need more time and cost consumption between the software, the CAE, and also maybe the user have a more design iteration by changing different tools. And also we might have the unstable performance with the thermal effect, and also it might having the error when we transfer the result between different tools. So the limited measurement and also the analysis between the tools also is a consequence to limit the design and having a big problem. So here is the example for the 6-channel WDM PAM4 transceiver design. So basically, with the design challenge to increase the transmission capacity and data accuracy, also keep at the low cost, the on-chip photonic and the core package optics are the very promising technology for now and the future. For it support the high speed and the high bandwidth equipment with low cost and low power consumption. So here we will discuss the design example for the workflow and our solution for the design challenge. So here is the workflow overview. For this design, we will start from the component. So the component tools will be like the FDE and charge, which is in numerical. We use these two solvers to simulate the behavior of the basic building block of the circuit. So the component we simulate in this solver will be like waveguide, ring resonator, and the modulator. So which is used in the transceiver design. And we get the properties of this component and save them in form of S parameter and so on to build the compact model in the circuit solver interconnect. So interconnect also the one of the solver in the numerical. And we also use the HFSS to do the RF radio frequency analysis on the board. Then also we save the data as in the S parameter and look into the interconnect to distort the electrical signal before we feed into the modulator. So we then use the optiSLang to we also use the optiSLang to do the co-optimization of the tool's performance before we feed all the data into the interconnect. So once the circuit view by all the components, we will use the IcePad to run the thermal analysis on the design board to get the thermal map, the temperature map. So we then use the interconnect again to run the circuit analysis. So this analysis will be analyze the performance and find the best allocation place to put the optical component. And we also use the thermally tunable component for the most temperature sensitive optical component, such as the modulator, to get the best circuit performance. So now we move into the first session, which is the charge and the FDE. Okay, so here is the photonic circuit block we will build inside the charge solver and the FDE solver. So basically, we will build the waveguide and the ring resonator, and also just now the modulator. So here is some example to make the charge simulation and also the mode simulation inside the charge and the FDE, and also the photo detector. So here is an example where we talk the light propagation on the video. At the right, so as we see, the light photon will transmit between the waveguide. So in the right side, they have a right angle of the path for the waveguide. So the return signal will be large compared to a round edge waveguide. So this we also analyze the fundamental of the TE and the TM mode for the waveguide. So one of the key component in this design is the traveling wave, the mass gender modulator. So we characterize the electro-optical behavior of this model by using the charge and FDE. So in charge, we simulate the charge transportation in the PN junction of the modulator, and we define the dropping profile of the modulator, then simulate the variation of the free carrier in the waveguide as a function of bias. So the equivalent circuit information is also simulated to define the electrical bandwidth of the modulator. So then with the dropping profile and the free carrier variation based on the bias imported into the FDE, we can simulate the optical index perturbation of the modulator based on the different bias. The nominal waveguide information about this model are also simulated in this FDE solver. So next section is the RF analysis section. So this I will pass to my colleague, which is Nicholas, to continue the following section.
Okay, thanks, Ro. I'm Nicholas, and next is the radio frequency analysis. So I will introduce the other tool for 3D electromagnetic full-wave simulations. It's called the HFSS. The HFS can simulate a 3D structure in the microwave or radio frequency analysis. This step we will run the radio frequency analysis of this modulator. So we do the cross-sectional profile simulations of the radio frequency transmission lines. So basically, you should using the charge to explore the resistance and the capacitance from the PN junctions. So they will be using the lump RLC boundary condition in HFSS. You can input this resistance and capacitance to these structures. And HFS will following this structure to do the full wave 3D simulations in electron simulations. And we can explore the radio frequency group index, port impedance, and radio frequency loads. They will be fed into the INTERCONNECT to define the modulator. So we also load in the electro signal distortions effect from the ball level. So if you want to more high accuracy simulation in result, you can use this to drive in the signal to the modulator. You can get the more high accuracy. So you can see that those figures will be more important information to emphasize the radio frequency interference for the other signals. So we can see the radio frequency group index and the return loss of the radio frequencies. Yes, next page. And if we want to finish the component simulations and the radio frequency simulation, we spice it up by doing co-optimizations of all the server to get the best component performance results. So there will be some file we need to be import to the optiSLang, and there will be the doping file and the electrode geometry file input to the optiSLang. And optiSLang will be output the radio frequency and optic group index and the loss and the bpi and the lpi files. So we can run the multi-object optimization to get the minimized velocity space and bpi, lpi, and the loss. And how can we do the optimizations? We using the elevations algorithm to do this optimization because the elevation algorithm is from the genetic algorithms. The spatially for this algorithm will be have the generations in these genetic algorithms. So they will be more powerful in the globally optimizations. And you can using this technique to do the multi-object optimizations. And we will do that so you can get the more high accuracy result with minimize those results. Yes. And next, you can see we can add to this design response surface, and we can see the all parameters relations and using obviously the MOP model to do the optimization is my efficiency measure to do this optimization because the MOP is like the raw models. You can see the many experience sample will extend in this space, and there may be the 300 sample in this space, and this 300 will be replacement of all the experience. And if we want to do the optimizations, we can firstly to find this 300 sample. If they have our solutions, we can judge more point and they will be close into these solutions to identify this is the local solutions or the global solutions for the optimization results. So they will be more efficiently because you do not like the other optimization tools. You need to do many experience. This MOP model will be used again and again, then will be extend more sample and for the other core, so they will be more efficiently measured to do these optimizations. Yeah. Next page. Okay, and if we finish the optimizations, we can identify the best designs. Maybe the parameters and of the waveguide and optical modulator and the traveling wave electrode are used to create a complex model of the modulator in INTERCONNECT. So the simulation bit error rate is used to identify. We can see the diagram and we can choosing which is the best performance for this designs. Yeah. So if we get that, we are finished the modulator simulations, and we can choosing the best performance model. and this model will build in the circuit. But before we jump to the circuit building, I have to say there are many issues in the board labels. The most important is the thermal issue. So the next page, there will be thermal simulations in these sessions. We can do the thermal simulation in iceberg. Let me introduce in iceberg. Iceberg is for the electrothermal issue simulations. It is located on the ATT platform. Just the interface is very similar with the HFS. So if you have learning the HFS at first, you want to use in iceberg, it's more easily to use in the other server tool. So we can judge our user to do this workflow to simulation the 3D structure or layer geometry in this interface. But now we want considering about the board label simulation and the modulator simulations. So we should be explore the some power make or some power device in these simulations because the iceberg just need the loss and as the source or the power as the source to do the temperature distributions simulations. So in this case, we are using this aspect to analyze the temperature on the wafer. The optical circuit will be put on the same board, and we want to find the best place to locate. We use 5 watts in the EICs, and the EIC heating could come from the CTM. Then the draw heat are improved from the SI wave. I usually set up the older board power map to do this setup. Sorry, we will should go back to the last page. No, please help me to go back to the last page. Yes, and we finish the board label power map. We are just into the 50 degree of the button on the board, and there will be set up the heat transfer coefficients on the top to generate the mesh and this corresponding temperature and information will be explored by the ACD or toolkit. Yes, the file will be in the next page. Please turn to next page. And this is the TXT file from the other toolkit to explore that, and we can get the locations and the temperatures, so we can see the power map to turn to the temperature distributions. They were including our modulator and the board label simulations. So this thermal simulation analysis will be look like this, and we have 4 more data to from the mesh for XYZ coordinated and corresponding temperature responsibly. We may notate the lead coordinated and to fix this file. And because the optical layer are very thin and compared to the other board label is very small and then the lead in these structures. So we should look at the temperature distribution to judge which location is the best choice in this design. Yeah, that's all the multiphysics simulation in this case. And I think the next we will turn to the optical part, and we will finish the optical circuit. So I will give this presentation back to the Lord. Yeah, thank you.
Thank you, Nicholas. Already present the section 2, which is the RF analysis, and then we go to the optiSLang to optimize the component and also the circuit. After that, we go through the thermal analysis to measure the thermal temperature map for the circuitry. So next, we will go into the interconnect. So this part is in the numerical, so which is a solver to do the circuit performance analysis. So here we can see, just now in the thermal analysis, we have a circuit board. So now we convert it into the circuit diagram, which is the schematic inside the interconnect. So we also import the data from the charge and FDE, and just now the RF analysis, and also the result from the thermal analysis ISPAC. So here we want to analyze the bit error rate and also the eye diagram of the optical board when we put in the optical parts or the component on different position of the board, the PCB. And also we want to do the best condition, the work condition for the ring, the ring modulator. So as you see here, here is the comparison when we put all the data into this interconnect. So, and we put here is the origin, which is the center of the PCB. So we see there is a higher temperature at this region. So this is a first simulation. We try to put the optical component on this location. So in the next, we shift by 7 mm in the x-axis and shift 1 mm in the y-axis, which is the cooler location compared to the previous location. So here is the 8 degree Celsius of difference between two places, and we make a comparison on the performance. So in the right hand side here, when we put on the hottest area, we have a worse BER, the bit error rate, and also the eye diagram is worse. So when we put in this cooler region, so we get a better eye diagram and also the bit error rate within the system. So here is the node for the tune ring modulator and also the resonator. It can help to get a better result under the current temperature. So here is the end of the presentation.